was discussing present worth analysis and analyzing projects. What we're going to do in this presentation and in this video is discuss annual cash flow analysis in analyzing projects. And the last week we discussed annual cash flow calculations, and we understand now that the difference between annual cash flows and a single present worth cash flow is simply a constant if you know the interest rate and the number of periods. So what we're going to do in this lesson is we're going to study annual cash flow calculations. We're going to understand how to analyze projects using annual cash flow analysis. And then we're going to discuss the period, the analysis period. If it's equal, and if there's if it's not equal, and if it's infinite. Finally, we're going to analyze loans and the present worth and what an annuity due means. So the first thing we're going to do is define uniform annual costs and benefits. And we're going to turn those into annual cash flow equivalents. And so we can have costs and benefits in present worth analysis that are a single point value. We can also turn them into an annual value over the life of the investment using the payment function, effectively using the formula. And there's really no difference between analyzing with present worth analysis or annual worth analysis. It's just differing by a constant, with the exception of analyzing a project, two projects that have uneven lives. And I'll get into that in a second. So let's talk about the nomenclature here. We have EUAC. That's the equivalent uniform annual cost. I will also refer to it as annual costs. EUAB is equivalent uniform annual benefits, and I'll refer to those as annual benefits sometimes. And EUAW is annual worth, equivalent uniform annual worth. And so sometimes I'll refer to this as the annual worth method. This is the annual cash flow analysis method. And so an example is we have a machine that costs $30,000, operating and maintenance of $2,000, save $10,000 a year. What is it annual worth at 10%? Now you should recognize this problem from the present worth analysis. It's the same problem. Let's look at this in Excel and how to analyze this. So here's our problem right here. And we can lay out our cash flows. And there's multiple ways to do these problems. I'm going to show you what I think is the easiest way, and then I'm going to show you a couple of alternative ways. So we have end of year. We have the cost. We have the savings. We have and whoops. Let's try this again. Savings. O and M. Salvage value. Net cash flow. We have an interest rate of 10%. Okay, so our cost I'll put these all in as dollars. Our cost, we're going to spend $30,000. Now I'm indifferent if you want to treat the cost as a positive value, as long as you subtract it when you calculate your net cash flow. Our savings is $10,000 per year. Our O&M is $2,000 per year. And our salvage value is $7,000. So our net cash flow is going to be the sum across. Actually, I did this wrong. Let's make this negative. That way we can sum it across. So this should look similar to our last example from last present worth analysis example. Now let's look at the PV factor. So it's P equals F over 1 plus I to the N. Oops. I'll drag that down because I tagged it. And so the present value of the cash flow is simply the cash flow times the present value factor. Let's tighten that up a little. Drag that down. $4,672.74. So that's the present value. The equivalent uniform annual worth is simply annualizing this. So you can do that with the payment function. Now our rate is 10%, our number of periods is 5, and our present value will flip the sign is 4672. So our annual worth, we are indifferent between these two. Note that they're both positive. A positive present value means a good project. A positive annual worth, equivalent uniform annual worth, means a good project. Now this is one way to attack this problem. Now let's look at another way. Let's look at the annual worth of the investment. And that's simply going to be annualizing this with the payment function. The interest rate is 10%. Let me back out of here. Let me put in a life of 5 years. I like entering numbers one time. So instead of 5, we're going to have that. That way, if I want to change things around, it's real easy. So if we annualize the investment, it's going to be the payment function. The rate is 10%. The number of periods is 5. The present value, remember this flips the sign, so we're going to put negative $30,000, and we're good. So $30,000 annualized over 5 years is $7,913.92 at the end of periods 1, 2, 3, 4, and 5. The annual worth of the savings is simply $10,000 per year because it's already annualized. The annual worth of the costs of the O&M is simply the negative $2,000 per year. It's already annualized. And the annual worth of the salvage value, now we have to annualize this $7,000. We can do that with the payment function. We use the rate of 10%. We're annualizing this $7,000 at the end of the 5th year over 5 years. Our present amount is 0, and our future amount, and we flip the sign with this, is this salvage value. So this is the annualized investment, savings, O&M, salvage value. We sum this up. We get the same $1,230.66. Either way is okay. I just wanted to show you, if you're analyzing this in industry, probably going to do it this way, the first way that I showed you. But if you look at textbooks going through the annual cash flow analysis, this is the way that they will show you how to do it. And so what they did here was in this example, this is annualizing the present amount. This is the annualized benefits minus costs. This is annualizing the salvage value. So it's like the second method that I showed you on that screen. Now, this is a terminology, and so it's basically the annual capital recovery costs. And when that is discussed, they're only talking about the costs of the investment. So the investment costs us $30,000, and we're going to get a salvage value of $7,000 at the end of the second year. Sorry, at the end of the 5th year. And so what we want to do is find out if the annual savings is going to be sufficient to recover this. So this is simply annualizing the upfront investment less the salvage value. If you look at this, remember there's 6767. There's the value right there. It's simply the annual worth of the investment, annual worth of the salvage value. If you treat it as a cost, then it can be positive. So you need to be really careful that you know what's going on so you can keep your sign straight. So what are we doing in annual cash flow calculations? We're turning a present amount at time period 0 into n equivalent cash flows of the same amount. And so notice that there's a difference of 1 period from period 0. So this first annual cash flow is not at period 0. It's at the end of period 1. That is the derivation of the formula. Now this is very similar. This criteria is exactly the same as present worth analysis. And it should be, because they only differ by a factor. And so if you, the typical situation is when you have you're comparing projects and they have different costs and benefits, you maximize the worth. You maximize the equivalent uniform annual worth. If they have the same costs and you maximize the equivalent uniform annual benefits, and if they have the same benefits, you minimize the equivalent uniform annual costs. So the only difference between this and present worth analysis is, instead of annual worth, it's present worth. Annual benefits, present worth of the benefits. Annual costs, present worth of the costs. So let's say we're looking at two projects right here, and we want to determine which one is the best to do. So let's do this in Excel. This is the way it would be done in industry. Interest rate is 7%. They have a different cost and they have a different benefit, so we need to maximize the equivalent uniform annual worth. First one cost $3,000. Let's see here. Savings. And I made a mistake. This cost $10,000. Savings is $3,000 per year. So our net cash flow looks like this. The present value factor is P equals F over 1 plus I to the n. Our present value is the net cash flow times the present value factor. Sum it up. $2,300. So the present worth equals $2,300. The annual worth, we annualize with the payment function. So this is alternative A. Let's look at alternative B, and we can do that real quickly with a simple copy command here. This is what alternative A looks like. Alternative B costs $13,500. And it saves $3,000 the first year, increasing by $500 each year. So $3,500 second year. And if we did this right, if I did this right with my copies, this is $300 more valuable, and the better alternative is alternative B by present worth analysis and biannual worth analysis. You have to come up with the same conclusion regardless of analysis method when you're comparing projects. If you come up with a different conclusion, you've done something wrong. And so you can see here that the equivalent cost of alternative A is $561. Equivalent cost of alternative B is $640. 561, 640. Recognize that they did it slightly differently than I did. They annualized, they used a gradient factor for the second one, a gradient of 500. I did not discuss the gradient factor. You will never use a gradient factor ever in industry. I've never used one. I have always analyzed projects in industry the method that I just showed you. Now, let's look at analyzing several projects here. We have 3 projects. They have an interest rate of 8%, a life of 10 years. We have an installed cost. We've got savings per year, operating expenses per year, and a salvage value. Now what we have here is we have a different way of looking at this. What they've done is they've annualized the benefits. So we've got our material and labor savings per year. That's the $14,000 right here. Then they've annualized the salvage value. Okay, that's the payment function with a final a future value in it. That's our benefits. Then they've annualized the installed cost, and then the operating expenses are already annualized. And so if we were to analyze this project right here, we would, if we were going to analyze this project with the annual worth method, we would say that Plan A has an annual worth of $3,869. Plan B's annual worth is negative, and Plan C's is $3,311. And so you would choose to do Plan A. And that's if your interest rate was 8%. Now this is one method of looking at this. And some companies might want to segregate their projects into benefits and costs when they analyze them. This is exactly, if you do this the way, well, let's just do one of these. I'll just do the first one. So we'll go over here, and this is our first one. Now this is going to be very similar. In fact, what I should do is this. I'm going to And delete this guy. And put this one back in. So what we have here is we have a life of, let me make sure I get it right, life of 10 years and interest rate of 8%. So 8%, these numbers are going to look screwy for a second. Life of 10 years. Okay, so let's insert 5 rows. So our first one costs $15,000. Our savings per year is $14,000 per year. Our annual operating expenses are $8,000 per year. Salvage value is $1,500. We'll drag down this net cash flow number here, and we will drag down this. So our annual worth is $3,868. Now, there's a very good chance that I didn't, here's where the problem is. This is F17. We don't need this guy. So this is Plan A. And clear, this is the way this would be analyzed in most of the companies I've worked with would analyze this project this way. And if they want to do the annual worth, they do it this way. Could do it this way. And what we did before, what they did in the example, is we have the equivalent uniform annual benefits, equivalent uniform annual costs, and equivalent uniform annual worth. And the benefits are the savings plus the salvage value, and the costs are the upfront amount annualized plus the annual O&M, and this is the way that it's done in the example in PowerPoint. Multiple ways to analyze these projects. Unless I ask you for a specific way, I'm fine with whichever way you choose. Now this example here is where we're going to analyze two pumps, A and B, with unequal lives. So if we look at pump A, it has a 12-year life, and pump B, it has a 6-year life. Now if we were going to analyze this using present worth analysis, what we would have to do is we would have to assume repeatability and assume that we're going to do 2 of pump B. Now let's analyze this, and I'm going to show you why annual worth analysis is better than present worth analysis when you're analyzing projects with different lives. So let's just look at what we do here. So we have two pumps. We have a 12-year horizon. They both provide the same benefits. So what we want to do is choose the one with the minimum cost. So let's look at what we have here. So we're going to do, I think that this is easiest to show with we don't need to go through the full-blown thing, we can just go with the cash flow. Okay, so if we look at pump A, we've got a 12-year life. And at the end of year 0, we're going to invest. This is going to be costs, so these are all costs. Oh, let's make it negative just so it's not confusing. And then we're going to have a 12-year life. Oops. And at the end of the 12th year, we're going to have a salvage value of $1,200. Let's see, I left out the interest rates. Let me just make sure I grab it. We're going to use an interest rate of 7%. So the present value factor is 1 over 1 plus I to the n. And the present value of the cash flows is going to be the present value factor times the cash flow. We'll just make this $1. Now, I just have to copy this down to here. Oops. And so the present value, it's a present cost of $6,467. Now, implicitly what's going on is we have zeros here. So we can drag these all the way down. Whoops. And nothing has changed. That's implicitly what's going on. So now let's look at pump B. So pump A, this is the present worth. And the annual worth is the interest rate. Whoops, that should be the interest rate, number of periods, and present amount. $814 for pump A. Now let's look at pump B. So we'll copy this. It's going to get messy till I clean it up. So pump B, it's going to cost us $5,000. Oh, this. And at the end of the 6th year, we're going to get $1,200 back. But we're also going to, no, $1,000 back, sorry. But we're also going to spend an additional $5,000 for another pump. So we're going to spend a net of $4,000. And then we're going to get this $1,000 for the second pump at the end of year 12. So this has a present cost of $7,221. It's got an annual worth in G2. Got to set the interest rate right. F19. So either way, we're going to be choosing pump A because it has a lower present cost, a lower annual cost. Just want to double check that my calcs are right. Okay, but let's look at pump B. We're assuming repeatability, and this is the power of doing a project with annual worth, doing an analysis. So let's just take one cycle on pump B. So this is what it's going to look like. And we're going to have a present cost of pump B of one cycle of $433.66. So this is the present worth. And if we annualize that over 6 years, look what happens. We get 909.18. So the conclusion here is that when you're annualizing, comparing projects using annual worth with different lives, if you can assume repeatability, you only have to do the calculation on one cycle. Why is that? Well, if you think about it, what we've done here is we've said our annual cost of pump B is 909.18. And so we're going to do that for 12 years. Well, that's really here's your first cycle. And here's the second cycle. Let's move it over one. We're going to go period 6 through 12. So in the second cycle, we're making this initial investment, and then we're going to get the same, because it's repeatable, we're going to get the same result. So this is exactly what we've done here. We've done this same thing again. So that's the power of doing a annual worth analysis. That's the best reason for doing it, is if you're comparing projects with different lives and can assume repeatability, you only need to do a single cycle. So what are we talking about? Here we have, if we have the analysis period is the same, we use that same analysis period. If we can assume identical replacement, we only have to do one cycle. And if we can't assume identical replacement, we have to estimate terminal values at the end of the analysis period. Exactly, terminal values being salvage values at the end of the analysis period, exactly like we did in present worth analysis. So again, if we were to do this with this project right here, we've got two pumps, A and B. One costs $7,000 as a salvage value of 15 for 12 years at 7%. So let's look at what we have here, pump A and pump B. I'll just cut this out because this is similar but not exactly the same as the last problem. Interest rate is 7%. Okay, 7,000, 1,500. $797.46 is the value. Now, so I've cleaned up pump B. Now I show it with a 9-year life, $5,000 investment in year 0, $1,000 salvage value at the end of the 9th year. And then I have the present value factors. I compute the present value, the present worth, and its present worth is a cost of $4,456. Now this is not directly comparable to the present worth of the 12-year pump because they have alternate lives. And to analyze it properly, again, we'd need to have a common denominator of 36 years. Do 3 of pump A and 4 of pump B. But assuming repeatability, we can just calculate the annual worth of each. So the annual worth of pump B, it's the payment, and the interest rate is 7%. The number of periods is 9, and the present value, it's a present cost of $4,456. This annualizes it over 9 years. And this shows that indeed pump B is a better choice because its annual cost of $684 is less than the annual cost of pump A. So this is the true benefit of using annual worth analysis compared to present worth analysis, is when comparing two projects with unequal lives. Now let's look at an example with an infinite analysis period. So let's say we want to compare two water projects. One is you build a tunnel for the water. You build it one time, costs $5.5 million, and it lasts forever. The second choice is to build a pipeline, and it costs $5 million every 50 years. And you'll have to do that forever. And so the concept is we want to turn this into an annual cost and compare the annual costs. Now the annual cost of the tunnel, if we remember our perpetuity equation from last video, P equals A over I. Therefore, A equals PI. So to annualize $5.5 million at 6% forever is $330,000 per year forever. Now, if we take $5 million today, and every 50 years, we can annualize the first $5 million. We come up with $317,000. And every 50 years, we're going to annualize another $5 million. And so we're going to actually have an infinite cash series of $317 million. So let's see how that works. So the tunnel, A equals P I think is fairly straightforward. And that's derived from the formula P equals A over I. The pipeline, we're going to annualize the first $5 million. And you do that by using the payment function. And the rate is going to be 6%. The life is 50 years. And the payment is the $5 million. So that's the $317,000 that we saw in the PowerPoint slide. That's going to be for the first $5 million for the first 50 years. When we annualize the next $5 million, we're going to come up with the same $317,000, and so on. So this shows that spending $5 million every 50 years if your interest rate is 6%, is about $13,000 a year better than spending $5.5 million up front. That's not intuitive. And there's, I would say it's highly likely that, that the $5 million in 50 years is going to be a lot greater. But let's do kind of a little what if analysis, just kind of a, so this is, let's make this a variable. Just move this down here and say this variable is $55 million. And so instead of having that as 50, let's make it a variable. Okay, so this is our base case. And now we're going to try doing some goal seeking. And what I want to do is find out how much different this $5 million has to be to make this value equal to $330,000. So what we do is we go into let's see if I can do this a little bit. I want to go into data, what if analysis, goal seek. And what I want to do is I want to set this cell right here to $330,000 by changing this cell here. And let's interpret this. What this is saying, this is with goal seek. If our pipeline costs $5.2 million instead of $5 million, we're basically a break even with the $5 million case. I mean, $5.5 million tunnel case. So that's kind of what I was talking about with the sensitivity component of this. Now let's look at this example. This is similar to what we did in the last video. And this is putting together an amortization schedule. So we've got a loan of $24,000, 6% nominal annual rate, 6 monthly payments. Monthly payments implies monthly compounding. So how do we deal with this? I like my way of setting up an amortization table. It's a little bit more detailed, but I think it's a little bit easier to follow. So we have an interest rate of 6% per year. That implies 0.5% per month. The amount we're borrowing is $2,400. So our payment, our monthly payment, is going to be 0.5% per month for 6 periods. And the borrowed amount, I'm going to flip the sign on it, so it'll be positive, is the $2,400. Our monthly payment is $407.03. Now our beginning period balance is going to be, at the very beginning, we're borrowing $2,400. Our payment is going to be $407.03. Whoops. Interest is going to be 0.5% on $2,400. 0.5% on the amount at the beginning of the period. And let's tag that 0.5% so we can copy it down. Now the principal, we're paying $407, so the amount we're paying on the loan is $407 minus the interest, $395. And then our ending balance is going to be the beginning balance minus the amount we're paying on the loan. Bingo. Ending period 1 balance is going to be the same as period 2 balance. Our payment is going to be this. Interest is a smaller amount. It's on $2,004. Therefore, our principal is going to increase a little bit, and our ending balance is going to be paid off a little bit more. And now they're all recursive. You can copy this all the way down, and I fully paid off my loan at the end of period 6. This is the amortization table that we're talking about. Finally, what I want to talk about here is prepaying a loan. How much is owed halfway through a 48-month loan of $15,000 at 9% nominal? Now, when you read this, 9% nominal means 9% per year nominal. You just have to know that. 48-month loan implied is monthly payments. So let's look at how we do this. So we have a 9% per year loan, implied monthly, that's 0.75% per month. We're borrowing $15,000. Life of the loan is 48 months. The payment is, using the payment function, your monthly payment is going to be the 0.75% per month, 48 months, and borrowing $15,000, $373.28. Okay, now at the end of 24 months, you will have made 24 payments of $373 and change. You have not paid off the loan at all. What you've done is, and you have not paid off, when I say paid off, you haven't paid off 373 times 24. Because there's interest in there. You also haven't paid off $7,500 because that's not what the, you're not paying off half of it, you're not paying off equal principal payments. What happens is after 24 months, you still owe 24 payments of $373.28 at 0.75% interest per month. Okay, that's the fundamental thing, and we find this with the PV function. So what we owe equals the present value. Let's flip the sign because I want it to come out positive. Okay, the rate is still 0.75%. The number of periods is the number of periods left. So we have 24 payments left. And the payment, we owe $373.28. That's how we get the amount owed. So at the end of 24 payments, we still owe a little bit more than half. We owe $8,170.68. Now this slide here shows you how to do it in 2 steps. Basically, we use the payment function to find the monthly payment, and then we use the PV function to find the balance owed after 24 months. So that concludes the lesson, this video lesson on annual worth analysis. Recognize that it's very, very similar to present worth analysis, and the only real difference is a difference in a constant.